All right, Chem, today we're going to do a bonding review. We'll start from the beginning and remind ourselves what we learned about bonding. First, we separated it into ionic and covalent. Remember, ionic is between a metal and a nonmetal. And it results in the exchange of electrons because metals are low electronegativities, nonmetals are high electronegativities. So metals become positive cations. So you will have a positive cation with the charge that indicates how many electrons it lost, and a negative anion with 8 electrons around it. Remember, in order to form a happy, stable ion, it has to have an electron configuration like that of a noble gas. And it will have a negative charge. So this is how we draw the structure of ionic compounds. An example, let's just do a simple example. Remember, we draw them with positive, negative. So magnesium has 2 valence electrons, which it will lose to have a charge of +2. Chlorine will get 8 electrons. Each chlorine has 7 electrons, can only take 1 more, so its charge will be -1. The positives and the negatives always add up to 0 because they are electrically neutral. Now, ionic compounds are all solids at room temperature. They're held together by electrostatic attractions. These are rigid crystal lattices, so they have high melting points and high boiling points. All solids at standard conditions. Then we went to covalent. Covalent is between 2 nonmetals. And for this one, we represent bonding pairs with dashes. Two dashes is a double bond. 3 dashes is a triple bond. A triple bond consists of 6 electrons, double is 4, and a single bond is 2 electrons. And then we also represent lone pairs with dots. So let's do a simple example of some nonpolar covalent. So nonpolar covalent would be, the only truly nonpolar covalent are the diatomic elements. So an easy way to do this is Br2 means that I have 2 bromines. Each bromine has 7 valence electrons. To get to 8, it would have to share 1. So they're going to have 1 shared bonding pair. And you can add up that Br2 has 14 electrons. You should represent 14 electrons. 2, 4, 6, 8, 10, 12, 14. All good. O2, oxygen's in family 6, so it has 6 valence electrons. So this has 12 electrons total that I have to represent. Remember, oxygen has 6 valence electrons. It wants to have 8. So it's going to share 2 in a double bond to get to that 8. And then this is 2, 4, 6, 8, 10, 12. And then N2 has 10 electrons. Each nitrogen from family 5 has 5 valence electrons. In order to get to 8, they'll want to share 1, 2, 3. Nitrogen is 3 positions away from the noble gas, so they'll share 3 pairs and they'll have a triple bond. Remember, nitrogen in family 5 is notorious, everybody in family 5 is notorious for having 3 bonding pairs in 1 lone pair. So this is how we do nonpolar covalent bonds. In nonpolar covalent bonds, there's no partial negatives, no partial positives, and they are held together by London dispersion forces. These are the forces between the molecules. So inside a covalent compound, the intramolecular force inside the molecule is covalent bonding. In between the molecules, or the intermolecular forces, is London dispersion forces. London dispersion forces can cause temporary dipoles. So that's to separate between ionic and covalent, and we've just gone over the covalent bonding, which kids tend to be, let's spend some extra time on the one that they tend to be most confused on, which is the polar covalent bond. Anybody have any questions about ionic and covalent? I want to point out to you, if you ever need any electronegativity differences at all whatsoever, I'm not going to make you memorize them. You're going to get them on the test. The other thing that we're not going to deal with, which is nonpolar covalent bonds, either are diatomic elements or they also could be caused by compounds that have symmetry. We're not going to go so far as for you to tell me when things are symmetrical or not. That's like kind of a next year topic. All right, now let's go to polar covalent bonds. Polar covalent bonds are caused by bonding between different nonmetals. So if you have two different nonmetals that are not in a symmetrical molecule, there'll be some level of polarity. Now, it's kind of an arbitrary scale, but remember we said electronegativity difference of 0 is only truly nonpolar, and those are going to be your diatomic elements. And we said 0 to 0.4 was going to be nonpolar. And then we said 0.5 to 1.7, again, just arbitrary, is going to be polar covalent. Anything greater than that will be ionic. So in polar covalent molecules, we're still going to use dashes for bonding pairs, dots for lone pairs, except this time we have to have partial negatives and partial positives to show polarity. So you're going to look at the electronegativity value. The higher electronegativity value will have a partial negative. The lower electronegativity value will have a partial positive. Let's remember electronegativity is the ability to draw electrons towards yourself in a shared bond. Fluorine has the highest electronegativity, and then you slide down, oxygen and chlorine are next, nitrogen, sulfur, bromine, so on and so forth. The further you are away from fluorine, the lower your electronegativity value will be. So the lowest electronegativity values are francium and cesium. So let's go over our two different kinds of polar covalent bonds, and that's going to be ones that have hydrogen bonding in between the molecules and ones that have dipole-dipole. So hydrogen bonding is fun. Hydrogen bonding is a special, strong dipole-dipole. I don't like the phrase hydrogen bonding because it's not really a bond. It's an intermolecular force in between molecules. So examples are, let's put this down, fun. So hydrogen and fluorine, HF. Fluorine has 7 electrons, hydrogen has 1, so we have to represent 8 electrons. I just represented 2, so I have 6 more. Hydrogen's already happy with 2. Fluorine wants 6 more, so this is what we get. The electronegativity value of fluorine is 4. Hydrogen is 2.1. That's a large difference, so that's going to be a polar molecule. These are 2 nonmetals, so we're going to call it polar covalent. And the more electronegative fluorine gets the partial negative, the less electronegative hydrogen gets the partial positive. Let's do H2O. Oxygen has 6, hydrogen has 1, so we have still 8 electrons to represent. 2, 4. Hydrogen can't take any more than 2. 6, 8. Oxygen is 3.5, hydrogen is 2.1, so we're going to say that oxygen is more electronegative, gets the partial negative. Hydrogen gets the partial positive. So remember, hydrogen bonding would actually be the intermolecular force between two different molecules. So we could draw it like this. The partial positive will be attracted to the partial negative on a different molecule. Let's try our last example, which is ammonia. Nitrogen has 5, each hydrogen has 1, so we're still representing 8 electrons, and we'll bond them together with 2, 4, 6. Have 2 more left over, which is good because nitrogen wants 2. Remember, nitrogen's in family 5. Family 5 is notorious for 3 bonds to get to 8 and lone pair. Nitrogen is more electronegative, hydrogen is less electronegative. So this is how we draw it. Remember, linear molecules always get 180. Tetrahedral molecules, which would be family 4, we'll draw the tetrahedral molecules next, is family 4 has 4 valence electrons, wants 4 more, so we'll form 4 bonds. And that's that 109.5. When you get a lone pair, it takes up just as much space and a little bit more, so this will be 107. And this will be a pyramid. Remember, tri is supposed to remind you of 3. So if you see 3 bonds at the central atom, you're going to say to yourself, are there any lone pairs? If there are lone pairs, you're going to say it's pyramidal. If there's no lone pairs, you're going to say it's planar. This has 2 lone pairs, so it'll be 105. And remember, this is not a straight molecule. This is a bent molecule. Let's add some hydrogen bonding in here just for fun. I kind of drew them goofy, but here, this would be the hydrogen and the nitrogen bonded together. That would be hydrogen bonding. Remember, these are intermolecular forces. This is an intramolecular force. Much stronger than intermolecular forces. Our next one is dipole-dipole. This is any polar molecule that doesn't have any fun in it. No fluorine, no oxygen, and no nitrogen, hydrogen bonds. So I can do an example. I always do the same ones. Let's do OBR2. Each bromine has 7, so 14 plus oxygen is 20. So let's put oxygen in the center because it occurs more often and makes more bonds. Bromine and all the other halogens and hydrogen are a dead end because they can only form 1 bond. Bond them together, 2, 4 out of 20. Now we satisfy the outside elements with 6 more each. That's 10, 16, 18, 20. Oxygen's in the center, so it's going to be bent. The bond angle is going to be 105. Dipole-dipole is also an intermolecular force between 2 different polar covalent molecules. So if you decide that a molecule is polar covalent, you got to figure out, is there hydrogen bonding involved? Is it fun? Is there no hydrogen bonding involved? Then it's going to be dipole-dipole. So we went over how ionic compounds are Solids at room temperature, high boiling and melting points, locked into rigid crystal lattices. Polar covalent molecules are held together with more force. Hydrogen bonding is next, then dipole-dipole. Those can either be solids, liquids, or gases depending on the size of the molecules. Bigger ones will be solids, smaller one will be gases. Truly non-polar covalent molecules such as fluorine, oxygen, and nitrogen. I'm going to add carbon dioxide in there because it's a symmetrical molecule. Those are always going to be gases. Okay, I'm going to add one more thing on there, and I'm going to let you guys do an activity and check answer keys. Any questions on that? Last part of this is I want to talk about the different types of bonding. We're going to start with metallic. Metallic is not a true bonding. That's why we don't draw structures for them. They are considered cations in a sea of mobile electrons, which causes all of the properties of metal. The fact that they are malleable, ductile, they're good conductors of heat and electricity, they're dull, they're shiny, they have luster. Did I miss anything? Sectility means that when you hammer into sheets, you can tear them. They tear even easier than paper. So we don't really draw those. Metals are all solids at room temperature with the exception of one. Anybody remember what that exception is? Mercury is the only metal that is a liquid. So these next go to ionic. Ionic are held together by electrostatic attraction between oppositely charged ions. This is the opposites attract. Or ion attractions. Now I'm putting these in order of strength without the metallic included. So polar covalent, we have hydrogen bonding, remember it's fun. This is an intermolecular force because these are true molecules now. And this is the strongest intermolecular force. It's a special strong dipole-dipole. Then we have polar covalent that is not fun, is called a dipole-dipole. That's next. That's for all other polar molecules that do not have fluorine, oxygen, and nitrogen in them with a hydrogen. And then we have nonpolar. These are held together by London dispersion forces, which can cause temporary dipoles. These are the weakest. Remember that if a molecule has hydrogen bonding, it also has London dispersion forces. If a molecule has dipole-dipole, it also has London dispersion forces. These tend to be solids. These are solids. These can be solids, liquids, or gases. And you might say, how do I know which? You don't have to know at this point, but you will later. And these are truly nonpolar covalent ones are typically gases because they have weak intermolecular forces. Remember, inter is between the molecules. Intra, inside, is the covalent ionic metallics type of thing. Okay, any questions about any of this? Yeah. And remember, this is your introduction to bonding. So you don't have to be super awesome at all of this bonding. You just have to be awesome at the things that we talked about in class. And then if you were to take a next year chemistry, you're going to review more about bonding. It'll become more and more clear. So that's a little summary of what you need to know for bonding.